Okay, we can start. And I want just to start from this video because let me see if I can turn off this. Okay, because I couldn't project it last week, and I think it is interesting. I just want to clarify one issue. Here you see that there is a flow duration curve. In the thick line is the undisturbed flow duration curve, and here basically you see with the thin line is the original one. It starts from the max and goes to the mean. The thick one is the usable discharge. So it's the duration curve of the usable discharge. And I think this should be clear. And the design flow is 1000. This is the run-of-the-river plant on the Po River and Isola Serafini. So here you have the downstream water level that corresponds to the different river flows. So for higher flows, you have a higher downstream water level, of course, because higher flow, higher level in the river. Low flows, lower level. And the upstream water level is kept constant because basically they open gates, they open and close gates in order to keep the upstream level constant. Gates that give access to the power plant, and a second gate that gives access to the meander. So in order to keep the upstream water level constant at the plant, they regulate with these gates the flow in the plant and the meander. So the upstream water level is constant. So the head is changing. For higher flows, you have basically it's changing because what happens is that for the higher flows, you have a higher level downstream, and therefore the head is lower. And in order to understand that this refers to higher flows, you have to look at the duration. Because of course the head is plotted on the vertical axis, but not on the axis of river flow. It's another axis that refers to duration. So on the vertical axis you see the head, and on the horizontal axis you see the duration that corresponds, shorter duration to higher flows. So here you have higher flows, lower head. Here you have longer duration, low flows, higher head. Okay? And now what's interesting is to see the power duration curve. I think, as I said, that this is a terminology that is a bit misleading because actually it's not a duration curve. It's a curve that shows the power depending on the river flow. So if we refer to a river flow with a duration that corresponds to 1000 cubic meters per second, this river flow, which is expressed in terms of duration, corresponds to a power that is the highest. It's the highest because with this river flow, we have the max design flow of the plant, so the max capability of the plant to handle water, to turbine water, with the head that is increasing with respect to higher flows. So basically here I have a head that is higher with respect to the head that I would have with higher flows, because I have the downstream water level that is increasing. So this means that with a river flow in the river of 1000 cubic meters per second, I have the highest potential hydropower production, because the plant is working at full regime, at its full capacity, and the head is decreasing for increasing duration. If I continue to increase the duration, which means that the flow in the river is decreasing, the head increases, but the plant is no more working at its full capacity. There is a lower flow going into the turbine, and therefore the produced energy decreases. So this is the way you should try to understand this graph. I think it is interesting, so this is why I want to get your attention, bring your attention to it. And this is typically something that I don't ask at the exam. I'm not asking at the exam, please tell me, explain to me this graph, okay? But I think it is interesting for you to try to understand it. Okay. Now, as I said, it's interesting that you look at these examples. And now let's turn on groundwater availability. And let me see, just 1 second, I don't remember if I made the PowerPoint available. Yeah, it's here. Let me refer to the PowerPoint, which is better. Okay, so let me now refer to groundwater resources. The problem is the same that we have to try to assess water resources availability by using inductive methods, by using observations, by using our knowledge of the groundwater body, knowledge in terms of information, not in terms of physical understanding of how it works. So what kind of observation do we have about water resources availability when we refer to groundwater? When we refer to surface water, we learn that basically we deal with the river flow observations. When we turn to groundwater, the problem becomes more complicated because groundwater is something that is more difficult to observe. I'm not saying that we cannot observe groundwater. We can observe it, but it's more difficult, of course, because it's underground. The river is visible. Groundwater is not directly visible, unless we see that there is an emergence of the water table. Typically, we see an emergence, which means that the water table comes to the surface when we see water sources or when we see other emergencies of water, and which are not really called sources. A source of water usually is something that delivers a small discharge. A source of water is the one that you typically see in the mountains when you want to fill your bottle of water, and these are sources that typically serve either single houses or small towns, and we call them water sources. There are sometimes other emergencies of water which deliver a more significant flow, and they are called in Italian risorgive or fontanazzi, something like that. But the essence is that sometimes we see some amount of water coming to the surface with a significant discharge. We usually don't call them water sources. We use other technical terms, which I'm sorry, I don't have the now. I learn in English how to call them. I cannot translate them now. Okay, but so unless we see an emergence of water, emergence I mean something coming to the surface, something emerging. So unless we see an emergence of water, we cannot see groundwater. The easiest way to see groundwater is to make an hole, to dig an hole in the ground in order to monitor at which depth we reach water. And typically these holes are excavated in order to withdraw water, and in this case they are called wells, okay, pozzo in Italian. But they are also very useful for looking at the groundwater level, at the level of water underground, the level of the so-called water table. When we see water table, we mean the water surface underground. We realize that this is very useful because by looking at the level of the water table in a well, we can understand the state of groundwater resources. For this reason, sometimes we excavate very small holes to reach groundwater resources which are not conceived for withdrawing water. They are just conceived to monitor the water level. They are called piezometers, or piezometry in Italian. The piezometer is just a tool to monitor groundwater level. So what is the purpose of observing groundwater level? The purpose is very clear. We found a groundwater resource, we start taking water, and after taking water, we want to monitor if the groundwater level remains undisturbed, not impacted by the withdrawal, or gets lower. If it gets lower, it means that we are depleting. We are taking more water than what is given by recharge, groundwater recharge. This is the technical term. Estimating groundwater recharge is extremely difficult. It's really a topical issue in general, not only with inductive methods. And therefore, this inductive way of estimating recharge is a very useful opportunity. As I said, we take water, we know the water flow that we take from the groundwater body. If we see that even by taking water, the groundwater level doesn't change, this may mean that the recharge is higher than our withdrawal, and therefore we can continue getting water. So it's a sort of trial and error procedure. We try, and then we look at what happens, and if we see that something bad happens, then we correct our strategy by reducing the amount of groundwater withdrawal. And these are called also, when these tests are made systematically in order to check the reaction of the aquifer to different type of stresses, these are called stress tests for groundwater resources. For instance, you may, after excavating a well, by referring a well, you may decide to try to take a lot of water, even more of what you need, just in order to test the capability of the aquifer to react to a stress. So these stress tests are often carried out by groundwater managers in order to understand what's going on, in order to understand to what extent we can push our withdrawal from groundwater resources. Actually, the situation is sometimes it's not so easy, because the reaction time of an aquifer may be very long. And if the permeability of the aquifer is high, if the aquifer has high permeability, then the aquifer reacts to disturbances in a relatively fast way. If permeability is very reduced, the reaction may be longer, and I tell you what I mean with an example. Let's suppose that you make a stress test on a groundwater resource, and you see that even after taking a limited amount of volume of water, you see a rapid decrease of the groundwater level. So your conclusion may be that, you know, the recharge is very limited. But actually, it may also be that the recharge is very slow, meaning that you know, the reaction time of the aquifer is longer, and some aquifer are recharged only in some seasons. And therefore, like during winter, they are recharged, and during summer, they are not recharged. So you may see a strong impact during summer, a decrease of groundwater level of water table during summer, but still it may be not concerning because during winter it gets replenished. The reaction time of the aquifer, as I said, it's different from that of surface resources, which means that, for instance, if you have a drought, surface water resources suffer from the drought immediately because their reaction time is quite rapid. So if during summer you have 3 months without any rain, you see rapidly the water level in the river decreasing. If you look at groundwater resources, you may not see anything because they react very slowly. On the other hand, what happens in the fall season, you may notice that the aquifer is not recharged, or the aquifer decreases after some months because the reaction is slower. So it's not really an easy task. And also, we referred implicitly up to now to the situation of an unconfined aquifer. If you look at this figure, you see that I refer to the situation of the upper aquifer. Let's assume that these two aquifers are separated by this dark blue layer, which is an impermeable layer, okay? Which means that they are physically separated, it's not the same water. And if we look at the upper aquifer, it's called unconfined. It means that the water table is has a direct interaction with the atmosphere. And in this case, it's a free surface. It's underground, but it's a free surface. It's an horizontal surface, and it's free because, as I said, it's a direct contact with the atmosphere. But it may happen that you have aquifers that are confined. Confined means that their upper limit is an impermeable layer. Their ceiling is an impermeable layer. And the recharge is taking place from somewhere laterally, maybe. And like, for instance, okay, let's like, for instance, from infiltration from the mountains. And the result is that this aquifer is under pressure, because given that it's confined, it has an upper ceiling. If we have water coming in laterally, and this water is coming from above, from the mountains, through confined channels underground, then the aquifer is put under pressure. Under pressure, it means that there is no free surface. And if we dig a well here and we make an hole in this confined aquifer, then water may come to the surface without any need for pumping, because it's under pressure. In this case, the aquifer is even more difficult to decipher. This is also called an artesian aquifer. Confined is a synonym of artesian. Artesian is more technical. Confined is more understandable. Unconfined, in technical terms, is called phreatic. And the wording is similar in Italian, phreatico artesiano. And as I said, the confined aquifer is even more difficult to understand because, you know, the recharge takes place typically from far away. And given that it's under pressure, it's not so easy to monitor its status, because we see water coming out spontaneously at the surface, and we don't notice whether the recharge or the storage, the total storage of the aquifer is decreased or not. Keep in mind that some of these aquifers are recharged so slowly that if we go with a well in the very deep ground, like 300 meters, we may get water from aquifers that were recharged like 2,000 years ago. And in this case, we don't notice we may not notice that the aquifer is going to be exhausted, because we take water, we don't see any decrease of pressure or water level. And when we start realizing that water is decreasing in terms of pressure or in terms of availability, then it is too late, because the aquifer may take 2,000 years to recharge. So this is a major concern, and people try to predict these situations by analyzing isotopes in the aquifer. By analyzing isotopes, we can estimate the water age. Everything is reported in the web pages, so take notes, but what I'm saying, everything is reported there. So they try to estimate the water age, because once you realize that you're using water that is 1,000 years old, you know, it may be a bit concerning, because once it gets exhausted, it's forever. Not forever, but for a long time. And in the same time, the water age may be 100 years, and still, it's a bit concerning. So this is to say that when we talk about inductive assessment of groundwater availability, science still has left some very huge question marks. We have some technical guidelines, but still, when we see that water boards or authorities are a bit concerned by the status of groundwater resources, I always reply that this is really a difficult issue to deal with, because in some cases it may be relatively easy. In some cases a stress test may be a good option because the aquifer is easy. There are some aquifers that are clearly easy. We clearly identify where water is coming from. We realize that water is just a few months old. So we realize that there is an annual cycle that completely replenishes the aquifer, but in other cases really it's a problem. And you know, in the same region, like the region here, you may have several aquifers at different depth. It's not only a problem of quantity, it's also a problem of quality. When the aquifer is unconfined, it's vulnerable to contamination. And the typical contamination is from agriculture, fertilizers, nitrates. And therefore, and keep in mind that to remediate, to restore an aquifer that is contaminated is extremely difficult. You understand why? Because it's a porous media that is very extended. Unless you have a very point source of pollution, a very point pollution, where you can try something. Otherwise, it's a problem. And therefore, the typical reaction of society is once that we realize that an aquifer is contaminated, and as I said, the most frequent contamination in agricultural regions is nitrates or phosphates, fertilizer. The reaction of society is to go deeper. And if we go deeper, so, for instance, in this region here, typically we take water for water supply systems at a depth of about 300 meters. And you know, when you go so deep, we have to be careful, because of course it takes more time for water to go so deep, and therefore the recharge time may be very long. We may use some what is called fossil water. Fossil water is perfect. I mean, it's very clean usually, because it was well filtered during its travel underground, but still it's a resource that may be exhausted. Okay, and this is inductive assessment of groundwater availability. There is nothing quantitative here. So we had to deal with this topic, inductive assessment of water resources. There was a part that is a bit quantitative, like flow duration curves, and a part that is less quantitative. And the quantitative, I mean less analytical. And this last part, you see that it's very descriptive. So it's not something that is really difficult for you to study. What I may call at the exam is what is a confined aquifer, what is an unconfined aquifer, and how can we estimate if withdrawal of water from an aquifer is sustainable. This is a typical question I may ask. Okay. By the way, did you try the self-assessment test, some of you? No? Not yet. Not yet, okay. Because I decided not to choose the option of being notified, because first of all, keep in mind that I think I already told you, I cannot see your names. I only can see your replies, but I have no way of seeing your names. And in order to prove it, I'll show you. Once you tried, I show you what I see. I want to make sure that it's crystal clear that they are anonymous. But I can be notified when somebody completes it. And last year I did it, but I got so many emails because the students took the self-assessment test like 100 times, and I decided not to be notified this time. But I am curious to know because, you know, sometimes I may make mistakes, and it's also technically not easy for me to set up these tests, and the mistake can be either conceptual or technical. And last year I made a couple of technical mistakes, so the evaluation of the marks was not very precise. So just let me know when you tried. Okay. I think we can move now to another topic, which is, it's more analytical, and probably it's, in terms of analytical complexity, is the more complex topic of our work together. And it's, again, assessment of water resources availability, but deductive assessment. And let me go to the related web page. I am downloading the PowerPoint in order to have it at hand. Okay. So, deductive assessment. What is a deductive method? I think I already explained to you what is. A deductive method is a method that starts from our knowledge of a process, and it's a so-called top-down approach. I start from the knowledge I build a theory, from the theory I build a model, and from the model I get the design variables that I need. It's different from the inductive. Inductive, I start not from the theory, but I start from the observation, which is another form of knowledge, by the way. And from the observations, I directly may estimate water resources availability without a model. Or even in the inductive approach, I may introduce a model like a probabilistic model, some probability distribution. But it's a model that doesn't start from knowledge, usually. First of all, keep in mind that when you have classification, I already mentioned it to you, don't have the requirement of putting each model into a category in a strict sense. Sometimes there are mixed deductive inductive methods. But if we want to make emphasize the difference, let me say again that the deductive methods start from knowledge. From the knowledge they build a theory model, design variable. It's applied in many instances in engineering. And if you refer to other subjects that you are taking, you may identify several deductive methods. So, it's, what is the advantage of the deductive method? The advantage is that it uses a kind of information that may be extremely useful, which is not by definition used by the inductive method. Keep in mind that you, as an engineer, you have problems to solve. And typically these problems are very practical, and these problems involve some societal exposure, some societal risk. This is typically the task of an engineer. The engineer usually doesn't study for the pure sake of knowledge. There are scientific disciplines where people study for the pure sake of knowledge. And there is no direct connection with the societal need, the practical societal need. There is the societal need of gaining knowledge, but not in all disciplines. There is a direct and practical societal need related to a risk. As an engineer, you are dealing with problems that are very practical and are usually related to risks for any type of intervention that you are designing. And therefore, you have an obligation to try to reduce the risk. Reducing the risk means reducing uncertainty. So you are obliged to use, you are called to use all the information that is available. If you have data, it is absolutely unreasonable to discard the information provided by data. If you have a theoretical knowledge, it is again absolutely unreasonable to discard the information given by theoretical knowledge. Keep in mind that this is, what I'm saying is extremely important because it allows you to identify the best way forward, and it allows you, once that you have to understand, to assess what others have done, it allows you to recognize what is a comprehensive approach, what is a reasonable approach, from what is an approach that is less comprehensive, less reasonable. It allows you, if we want to be very specific, to distinguish the fake news from the real news. Because, you know, sometimes you can clearly recognize in a fake news the fact that a type of information was discarded completely. Either because somebody declares that doesn't have faith on this type of information, or even if it's not declared, you can recognize that something goes wrong because there is an information that is discarded. So sometimes you see people saying something that is contrary to your theoretical knowledge. It means that these people discard the theoretical knowledge. Okay? So some people say that the earth is flat, you know, no? They are called in Italian terra piattisti. And of course you can clearly recognize that they discard part of the theoretical knowledge, and therefore the question should be, why are they doing that? They do that because they have a good reason for doing so or not. In this case, you can clearly conclude that they don't have a good reason for discarding this theoretical knowledge. And so you can easily say this is a fake news. Okay? If somebody says the earth is flat, you can clearly say this is fake news. But there are other examples where, you know, it's not so easy. And therefore, my suggestion is look at whether or not people have used all the available information. So sometimes you listen to people saying, I discard the data because in my opinion they are not meaningful, they are affected by too much uncertainty. So is this reasonable or not? In some cases it may be reasonable. In some cases, if they provide a good motivation, it may be reasonable to discard data. But if there is not a good motivation, it's absolutely unreasonable to discard data. And in this case, for instance, I am referring to the climate debate. And you know that some people make predictions based on model, and other people make predictions based on observation. And usually people that trust in models, they say, I don't trust data because there is too much uncertainty. I don't think this is reasonable. And people that just trust data, they say, I don't trust models because they are not reliable. Unless they provide a good motivation for stating that, it's not very reasonable. So you should look at a mix of the two, and you should in particular look at whether or not, again, I am repeating what I just said, all the information is used. Okay, so in deductive methods, use a good piece of information, which is our understanding, our theoretical knowledge. And typically, these deductive methods use models, and you see here that the first paragraph of my webpage is rainfall runoff modeling. Rainfall runoff modeling means that I start from the observation of rainfall to estimate runoff. Instead of looking directly at runoff data, runoff is river discharge. Okay? It's more or less a synonym. And instead of looking at river discharge, I look at rainfall, and through a transformation model, I estimate the river discharge. This is very useful if we don't have data of river discharge, but we have data of rainfall. This is very useful. So we need to build a model. And the model is something that you may As an engineer, I think you should be confident with mathematical models, but still, we are not much confident with mathematics, and you may be concerned by the word mathematical model. I suggest you to not to be concerned, because as you will see, some of these models are very simple. And in any case, you don't have to be concerned, because as an engineer, of course, your theory gives to you the means to build mathematical models, and therefore let's try to get more confident with them. Okay, let me go to the presentation. And let's refer first to surface models, surface water resources. Okay, again, let's make a difference. And let's refer to surface water resources. And therefore, we refer to what, as I already mentioned, what they are called rainfall runoff models. Why a rainfall runoff model is useful, I already mentioned to you. Rainfall data are much easier to collect with respect to river flow data. And the reason is that for observing rainfall, it's just enough that you put a tank outside, and every day in the morning you go there and measure the depth of water in the tank, and then you empty the tank, and the next day you go there and repeat the measurement. And this is what people actually did. Typically, this was done by priests and monks, because, you know, they were dedicated traditionally and historically to observing nature, observing the earth, and also they had time. But, and this is strange, humans didn't have the intuition to observe rainfall until 1600, more or less. And this is really strange, because humans had the intuition to observe stars, probably because they needed it in order to navigate in the sea, probably. Or they had the intuition of studying mathematics thousands of years ago.